if we had listened to Phil Curtis way back then, there never would have been math wars. He not only understood so much, but he understood how to listen to people and make sense of what they were saying, even when sometimes it didn't make sense. How can I lower it? Maybe I'll just lower this. Sometimes analog works. Does anyone know why this is up here in the speaker? It's a little... Well, you know that problem where you're given the radius and you have to deduce the length? Okay. I'll stand over here. Many of you have seen me speak before, either in person or on video, and I'm going to have a portion that's the same that I always do, because it's sort of basic building block. And then I'm going to go more deeply than my usual talk, because of the sophistication of this audience from Barrett School District and the surrounding LA area. Okay, so the Common Core standards were written to solve an education problem, not a political problem. And one of the unique things about the conditions under which we wrote these, which unlike the conditions for writing California standards or any other state standards, was that the... Is this the sound?
Yeah.
Let's turn it down a little bit.
Yeah, that's what I was thinking.
All right. That's good. How's that? Can you hear me in the back? Yes, all right, good. Usually you get people, 40 people in a room, they take turns making speeches, stuff goes up on poster paper. If they disagree, it's okay, there's plenty of poster paper. And in the end, you wind up with something that commemorates a political process. And in this case, none of us wanted to do that. Any of us who had experience with standards knew that, and I wouldn't have been part of it if it was just that again. And so this was set up as a design process rather than a political process. And since it was being sponsored by the National Governors Association and the chief state school officers, the governors said, we'll take care of the politics after you're done. Just design something that works well. And so we had a kind of conditions that to work in that were much better than normal for producing something that worked as a tool. And that turned out to be important. So our mantra at the beginning was, this is based on evidence, not politics. And these were our sources of evidence. High-performing countries like Japan, research, and lessons learned from 30 years of standards-based accountability. It was my own view that it's time to move on from what we've been doing for 30 years, especially No Child Left Behind. And but that's a different talk. So what did the evidence show? In the evidence here, because I'm going to refer again to high-performing countries, I want to clarify what I'm talking about, because I know it's irritating to be compared to countries where conditions are so different. So I want to first state what the data actually say, which isn't what the newspapers report. The newspapers report U.S. lags behind rest of the world. That's not what the data say. The bad news for the U.S. is mathematics specific. The results for science are different. The U.S. is slightly above average in science. And in reading, the U.S. is among the higher countries. It's in math. Same kids, same teachers. So that's number one. Number two, what the data show is there's a half a dozen Asian countries that outperform the rest of the world. And we're part of the rest of the world. On the two tests, TIMSS, which is school mathematics, grades 4 and 8, and PISA, which is age 15, which is out-of-school mathematics. In other words, using math to do things in the world. Very different kind of test. On those two tests, you get different rankings of countries. So, for example, on TIMSS, we always outperform Germany. for example, and Sweden and Norway. Not Finland, but we do outperform them. On TIMSS, France has done so poorly that it stopped taking it. So there are many European countries that we outperform on TIMSS. On PISA, Germany does very well. Northern Europe is very proud, and rightfully so, of their programs for what they call the polytechnic programs, for the people going into technician jobs, not four-year college, but two-year college and other technician jobs. They have very serious programs on which many good people and lots of money are spent for kids who are not going to college. And it shows in their PISA results. Doesn't show in their TIMSS results. So we have these half a dozen high-performing countries, recently joined, incidentally, by Canada, which has increased its scores. Used to be close to us, now it's close to Japan. And Finland on TIMSS, which is the best country in Europe. But we're not catching up to these competitors. At the same time, NAEP, the National Test of Educational Progress, designed very carefully to measure trend. And so from one test to the other test, they do everything they possibly can to make the measurement of trend precise and accurate. It's the best measure of trend in the world. That's its sole purpose. On that test, there was one form which is given since the 70s and still is given every 5 years to a national sample. Every decade has outperformed the previous decade. And so many students now on that test are getting most of them right that they're talking about having to either stop that test or do something else. The other NAEP, which is the one that gives us state scores, and that's the one that tells us California is a low-ranking state, that test started in the late 80s. And on that test, which is much more comprehensive in terms of the curriculum, that old test from the 70s is really just arithmetic problems. The one that started in the 80s has geometry, data, algebra, number, a full spectrum. On that test, every decade is better than the last. So what this is saying is kids like you that are in school now know more math than you did when you were their age. You would not get that from reading the paper. So here we are doing better than we ever have, but we're not catching up to the competition. If we were a business, would we say, they're beating us, let's go back to what we used to do? Or would we say, let's see what they're doing and figure out what we want to do about it? And it's in that spirit that we, during the writing of the Common Core and subsequently, have looked closely at what countries like Japan are doing. And you'll learn more about that. So what did the research say was wrong with the U.S.? Well, there was a study from the second international comparison, SIMS, which addressed that question directly. And the title of that report was The Underachieving Curriculum. Not the underachieving students or the underachieving teachers, principals, parents, schools, but the underachieving curriculum. And it came to the conclusion, which we've all heard, the curriculum is a mile wide, inch deep. Now, it's not saying that teaching can't be better. Teaching can always be better. It's saying that teaching is very variable everywhere in the world. As far as I can tell, there's only 3 countries that are consistently done something to make the overall level of teaching distinguished from the rest of the world. That's Finland, Singapore, and Japan. And in the case of Finland, just so it's not a mystery, Finland and Singapore followed the same strategy. They made the number of teacher preparation slots very small, and they made it very hard to get into teacher prep. And so it was competitive and selective to get into teacher prep. And once you get into teacher prep, during your undergraduate years, you study a lot of teaching. You don't major in something else. You're majoring in teaching. And then when you get into the schools, there's an apprenticeship program. So you're not teaching in Japan, it's a lesson study. That's the main. Singapore has both. So the finding was that our curriculum is a mile wide, inch deep. What does that mean? And I want us to dwell on this, because there are two ways in which our educator brains go to sleep on this one. One is we always assume that the problem is the way we're teaching and the solution is professional development. That is not what the research says. It doesn't say we're teaching great. It's just saying the thing that we're worst at compared to the rest of the world is our curriculum. And what's wrong with it? Mile wide, inch deep. That's one of those phrases where, well, I know what it means. I don't have to think about it. So when we were trying to think about it, we realized we hadn't really thought about what it meant. And you can get yourself to start thinking about what it means by asking the question, who's doing this to us? And after a while, we eliminated the theory that it was the North Koreans' secret plan. We realized the only answer to that question is we must be doing it to ourselves. So one of the things I want to do today is help you understand this problem, and particularly how we as teachers are doing it to ourselves. It's not the teachers alone. It starts with the state, the publishers, district offices, and everybody's contributing their share. But teachers are part of it too. And I'm going to emphasize that because that's who we are. The causes and the cures. Well, the easiest way to start is to look at this more mathematically. Mile wide, inch deep. That's a kind of an additive way of looking at it. And that's true. It's too wide and too shallow. But there's a more multiplicative way. Too little time per concept. Japan spends a week and a half on a concept. We spend 2 or 3 days. Is there some magic reason why more of them are learning it and they're learning it more deeply? They are spending more time per concept than we are. More time per problem. How can they do this? Do they have really long school years? Really long school days? No. They have less concepts and they do less problems. It's a rate problem. More time per topic requires less topics. Well, that was good for us as standards writing, and standards writing is much easier than writing a curriculum, I can tell you that, and it's certainly much easier than teaching and making the transition to the Common Core. So I will confess that I know we did the easy part of the job. So we look for topics to delete. And the essence of the mile wide, inch deep is that our curriculum has a lot of junk food in it, which is different than saying it's incorrect. It's just junk food. And it has a lot of redundancy in it, and it has a lot of incoherence. And we found all those things to be true. When we looked at the state standards, and we had computer systems to help us look at all 50 states fairly quickly, and we had little research assistants helping us. And we had access to the ACT and College Board databases, which I'll mention some interesting things we learned. So our first thought was, let's find some bad topics that lots of states are teaching and delete them. And we didn't find any. What's in state standards is all good stuff. So we decided and had to face the fact we had to delete good topics. What we found is that within the topics, there was a lot of junk. So if you want to see what we cut out, you can't do what some people have done, which is to count standards. You have to read what the standard says about the topic, not just see what the topic is. Because that's where the biggest changes are. But what we found, and it's just some examples, we did reduce the amount of data in elementary school. And this was not because we didn't like data, we love data. But we decided that the path through arithmetic to algebra was the top priority. And we were going to make that path coherent. And that the other topics in mathematics would have to adhere to that coherence. And so in the end, there wasn't enough time for systematic development of data through elementary school. So does that mean you're not allowed to teach data in elementary school? No, we still have data, and data can be a useful way of teaching arithmetic as a context. But in terms of is data an important goal of grade 3, it's a minor goal. Many states complained because kids love data, and teachers who love kids love data. And, why? They thought we forgot, but no, we had to do some painful things. Just a few others. What we found is coherence was very fruitful. If you're teaching in a superficial way, then each time you introduce a new kind of problem, you teach a kind of special purpose method for solving that problem, which might be the best way of solving that problem, but it's not related to the way you're going to solve other problems later. And if you go a little deeper, that's more general, you can actually get away teaching a lot less stuff that coheres a lot better. So we found a half step deeper, which is where the curriculum was written in Japan, Singapore, and elsewhere. It was more coherent and there was less stuff. And I'll give you some examples of that. But first, let's look at an example of some things that are not in the standards. Simplifying fractions or putting fractions into lowest terms are no longer in the standards. Is that because simplifying fractions or fractions in lowest terms are incorrect? No, they're not incorrect. It's because having the teacher lead the kids down those alleys leads them a place which is really a cul-de-sac. It's not going in the sense of direction that we had. So it's kind of incoherent. When you work with fractions, the more important idea is changing fractions into equivalent fractions. What we've seen in the curriculum is the teachers teach 2 or 3 lessons on equivalent fractions. It doesn't relate to anything else, and then they move on, and they spend more time simplifying as though it was a different topic. In fact, when you do arithmetic with fractions, you're almost always going in the opposite direction, changing fractions so they have the same denominator. You don't simplify them to make the denominators the same. You go in the opposite direction. You change thirds to twelfths. When you get to percents, you change everything to hundreds. So simplifying, we felt, was the wrong sense of direction. It's not prohibited, but it's not required. It won't be on the test. All right, so this is our quiz. I'm sure some of you have seen this before because I give this quiz every semester. We know, this is California, we know how to take multiple choice tests. So we know we're supposed to choose this one. Most parents and kids believe it's this. When you stick your head in most American classrooms and you hear that ch-ch-ch sound, what'd you get? How'd you get it? It's as though this were why we were giving them problems. As though we were giving them problems so that they would give us the answers. In Japan, the answer comes out, they spend another 10, 15, 20 minutes on that problem after the answer. In America, you get the answer, on to the next problem. They spend all period on 3 problems. We do more problems than any other country, by the way. We do lots of problems. And as kids, when you interview kids, this is from some tapes I saw of interviews, they point out that when one of the kids gets the right answer, the whole class moves on, even if some of the kids didn't get the right answer. So in that dynamic is another feature of how an answer-getting concept of curriculum exaggerates the differences among students. I want to come back to that. So I'm not saying answers are bad, and no, on the contrary, answers are good. Getting answers is good. What I'm saying is it's more than good. It's necessary. It's at the heart of what we do in mathematics. I'm saying it's part of the process. It's not the product. The product is the mathematics you walk away with at the end of the chapter. It's not the answers. And we have to shift our focus to getting that product. And not only the correctness of the answer is essential, but incorrect answers can be an important part of the process. What's your name, sir? Ramon. Ramon discovered a way of thinking about this problem that didn't work. Ramon, explain your discovery to the rest of the class. Class, let's figure out why Ramon's way of working didn't work. Ramon, any ideas? Ramon will have ideas because he's been thinking about it. You see that almost every day in a classroom in Japan or in Singapore. I asked Akihiko Takahashi, who's now a friend, who spends half his year in Tokyo and half in Chicago, so he knows our system. And I said, what are they doing? Why do they do that? He goes, in America, you think there's something wrong with Ramon, and you want to move Ramon over to the wrong answer table, and you want to find everyone else who had the wrong answer and move them over there. And then you want to hit them over the head with the differentiation hammer. He said, we don't understand what you think you're doing and why you think something good will happen when you do that. So you're making a lot of assumptions that are hardly ever true. First, you're assuming that everyone who got the wrong answer for the same reason. And you're assuming that the reason they got the answer wrong has something to do with gaps in their mathematical education. It's more likely it has something to do with unlucky assumptions that Ramon made, or reading difficulties with the problem, or something else. It'll be a different reason. You don't know the reason. And, he said, you don't have to know. He said, and even worse, you're assuming all the kids who got the right answer because they understood the mathematics. Most of them got the right answer because they made lucky assumptions. They make assumptions like this. We're in the chapter on set up proportions and cross multiply. Therefore, I don't have to read the problem. I don't have to understand the mathematics. All I have to do is, I know which numbers go together. Just there's 3 numbers there. I just have to set up a proportion and cross multiply. And I'm getting an A on the test at the end of the chapter. 2 years later, or even at the end of the year on the state test, I'm not in that chapter anymore. Those assumptions are not going to work for me. I don't know what to do because I didn't learn the mathematics. These are all good things, and they're not competing because they help each other, all these 3. Today, I'm focusing on number 3. NCTM and others have really worked on number 2. And so as a country, we're doing a better job on number 2. That's what PISA is mostly about. Number 3 is where we have a pathological blind spot and where the Asian countries are so good. Making sense of the mathematics you learn from working on the problem. But it's a habit, and it's going to feel like a habit. Kids will push back. Just show me how to do it. My own daughter, helping her with geometry. Daddy, I don't have time to understand it. I just want to get it right on the test. Why does what she said mean anything? It means I understood what she meant. It should be meaningless, but it isn't. We all laugh. Okay, so American teacher preparing a lesson. How can I teach my kids to get the answer to these problems? Japanese teacher, how can I use this problem to teach the mathematics of this unit? Just because we have different questions doesn't necessarily mean they have different answers. Mathematicians know that. But these two questions do have different answers. I'm an American teacher. My job is to teach you how to get the answer. Some of you are doing algebra. Some of you don't know the multiplication table. Some of you aren't paying attention. You're all over the place. So you want me to teach them some mathematics, then show them how to use that mathematics to solve this new kind of problem? Some of them will learn the mathematics, but they won't understand how to use it. Some will. Some will be confused, and they'll still be trying to learn the math while I'm having them work on the problems. Some of them will get confused and quit. Some of them are so used to being confused they won't even start. This is a classroom management nightmare. I got a better idea. I'll show them how to get the answer without having to learn any more mathematics. I'll just show them an answer-getting trick, like this one. The butterfly method for adding fractions with unlike denominators. I've used it. I'm sure you've used it or something like it. We draw the wings. We draw the body. We're going to multiply on the wings, but first we put a plus sign for an antenna as a reminder. Multiplication time on the tail. And now we go ahead and we multiply 4 times 1. It's 4. We write it down. 3 times 3 is 9. I write it down. There's my reminder. 9 plus 4 is 13. I write it in the head. I come down here. It's multiply. 4 times 3 is 12. I write it in the tail. Answer, 13/12. Takes 1 day to teach kids how to do this. They'll get the right answer all chapter long. But what the heck does this have to do with mathematics? Within months of learning this trick for getting those answers, they're going to be learning a trick called invert and multiply. And then they're going to be learning set up a proportion and cross multiply. They all have fractions and they all look like this. What's going to be in their heads 2 or 3 years from now when they're taking algebra? This is the foundation for confusion and misconception. It's not the foundation for algebra. The California framework, I had the funny experience in Chicago of watching Akihiko and 2 other Japanese mathematics educators explain the Common Core standards to American teachers. It was a room bigger than this. And they didn't know I was in the audience or who I was, so I thought this would be good. And at one point, Fuji Sensei, which means Master Sensei, Master Fuji, put up the standard from Illinois and a standard from the Common Core standard for 5th grade adding fractions with unlike denominators. And he asked them what they saw. And the answer he got back from everyone was, they're the same. 5th grade, add fractions unlike denominator. And he paused, and it was a Japanese pause, so it lasted longer. He said, you're blind. Read what it says about adding fractions. And the Illinois standard was more or less the same as the California standard. It said something like, and this is what the California standard says, that 5th grade teachers will remember, add, subtract, multiply, and divide fractions including mixed fractions and decimals including real-world problems or something like that. In other words, it was just telling you what kinds of problems kids should get the answer to. The Common Core had a standard unique to adding and subtracting with unlike denominators. And it said, change fractions with unlike denominators using equivalent fractions to make fractions with the same denominator and add them. In other words, it was describing the mathematics, not telling you what kind of problem to get the answer to. And it wasn't mixed in with multiplying and dividing and decimals and mixed fractions. The coherence we built around fractions, by the way, was, if you read what it says, and there are many more fraction standards than there used to be, because we were very explicit with fractions, it does reduce the amount kids have to learn about fractions. One of the great sources of incoherence in our curriculum, unnecessary sources, was we taught an arithmetic of whole numbers, and we pretty much extended that same arithmetic to numbers with decimals. But then when fractions came, we taught an entirely different arithmetic for fractions. And in fact, the arithmetic we taught for fractions, we taught two arithmetics, one for adding and subtracting and one for multiplying and dividing. And then when we introduced letters and expressions with letters, we taught a third arithmetic. And we noticed that in Japan, they taught one arithmetic and taught kids how to extend that single arithmetic to new objects. How do you use whole number arithmetic with fractions? How do you use whole number arithmetic with letters and expressions with letters? How do you use it with rational numbers and the reals? So the kids only had to learn one arithmetic, and they were well aware, because it was in the foreground of their curriculum, that they were building this new knowledge on their old knowledge. So what we did is start the fraction curriculum with unit fractions. Third grade is just understanding what unit fractions are. And if you think about what a unit fraction, 1/3, 1/4, 1/5, they're units. So 3 apples plus 5 apples equals 8 apples. In that statement, apples are the unit. 3 inches plus 5 inches plus equals 8 inches, and that inches are the unit. They're what you're counting. If you can count them, you can add them. Well, you can count unit fractions. 1/4, 2/4, 3/4. They count just like apples. And you can add them just like apples, using the same arithmetic you already knew. Don't learn a new arithmetic. 3/4 plus 5/4 equals 8/4. If you can count them, you can add them and subtract them. There's nothing new to learn here. The only thing you need to learn is that you can create something that you can count by partitioning the length from 0 to 1 into 4 equal parts. And the length of that part is 1/4, and the name of that number is 1/4. So already in third grade, 1/4 is a number. We don't learn its division until 5th grade. It starts as a number, and it starts as unit fractions. Now, all we need to do, because sometimes we have to add thirds to fifths, all we have to do is figure out how to make thirds into fifths into fractions that have the same unit fraction. That's what equivalence is all about. And equivalence comes down from algebra. And, what do you do in algebra? Change an expression to an equivalent expression. Change an equation to an equivalent equation. And hopefully when kids are working on solving equations, they're doing it by treating each step as equivalent equations. So we take from K1, 2, 3, whole number arithmetic, build fractions out of that solid ground, and aim for algebra. And from that, we get a much more coherent path with less stuff in it. In fact, what we did is even more elegant than what the Japanese and Singaporeans did. I was invited over there to visit schools and, of course, give a talk or two. When I got to Japan, yes, I visited lots of schools. Akihiko was there at the time, and he was my guide. But the talk or two that I was supposed to give were meetings with their standards commission. Only they don't call them standards, they call it syllabus. And they have a commission that is seated for the full 10 years between their revisions. And during that 10 years, they are visiting schools and classrooms to see how the standards are working. And so when they revise it, it's based on how well the previous version worked. It's not based on handsome postures like here. And they had studied the Common, I can tell you that commission understood the Common Core better than any of our states. They knew things about them that the writing team didn't know. But they were very interested in the fraction part, and they'll be revising theirs to bring it in more alignment with the Common Core, especially the fraction section. Singapore as well, Mexico as well, Italy, Poland, England, maybe, maybe not. All those countries, Thailand, they send their kids to our universities, and many of them naively think we're teaching the Common Core standards, and so their kids need to learn them too to keep up with us. We did this to catch up with them. They know what we're doing better than we know what we're doing. In fact, the guy in Singapore told us, you want to know what the magic pill is? Everything you see in our classrooms, we got from you, or Japan. We do it, and we finish. If you want to get results like ours, just do what you say. Finish what you start. FOIL method, another. Who hasn't used the FOIL method? I taught the FOIL method. What's wrong with it? It works all chapter long. Next chapter, you get a binomial times a trinomial. It doesn't work. It takes one day. What we should be teaching them is how to extend what they are supposed to know about the distributive property to expressions that have exponents in them. It's an extension of something they should have learned in fourth grade, and therefore an opportunity to teach them what they should have learned in fourth grade, which is the distributive property, which, by the way, when you talk to university faculty, they will tell you, stop teaching AP calculus and teach the distributive property. Because they're getting kids who pass the AP exam who come into calculus and make, especially distributing a subtraction, a negative number across a subtraction. If you're going to teach it focusing on the distributive property, which is what the Common Core say you should do, it will take 2 or 3 days. And you won't get the answer as fast. And it will use more paper. All right, I just want you to work on this problem. I'd like you to work on it solo for a minute, and then turn and talk to your partner about the different approach you use to the problem. Well, you're supposed to be solo. Why is all the talk? Oh, there's no problem. Very common to see in Japan, they take a piece of paper and tape it over the question that has the answer. So you only see the part of the problem which has the data in it. They do that because they want to postpone the answer-getting response, the answer-getting behavior. It's an issue there, too, by the way. This wanting to get the answer is a normal human response. It's not, we didn't invent it in America. So they have this method of just hiding it and spending a minute or two, whole class, discussing what's going on here. And this is deliberately a very simple case, but you can imagine a more complicated problem that is worthy of more discussion. And the gist of the discussion is basically to make sure the kids comprehend the text, not to show them how to do the answer, and understand what quantities are being referred to. And then sometimes they'll do something we tried out in San Francisco and Oakland, and it worked across honors classrooms and remedial classrooms, the whole thing, which is to ask the kids to write a question that uses this and makes it into a word problem. So I'm going to ask you to do that right now, and I'll just spend a minute alone making up a question that turns that into a word problem. No need to be creative for this. Just a simple question that makes that into a word problem. Then I'm going to ask you to turn and show your question to your neighbor. Okay, let's get back together. Let's get back together. Let's just hear a couple of questions from the audience. So, the woman in that nice pink blouse back there, sweater, what was your question? There's a woman, is that pink? What color is that? Orange. How long did it take to run what? Okay, so how long did it take? Okay. All right, how about another question from over this side? How about the LA Dodger fan over there? If you don't want to get called on, don't wear hats. So what did you come up with? Pardon? Oh, so he's going deep. How would you graph the seconds and the meters at the same time? Oh, these are interesting. Yes? How long did it take to run 50 meters? How many had a question like that? How long did it take to run a given distance? Quite a few. Did anyone have, how long did it take, how far could he go in a given amount of time? It's about the same number. And then some of you like that, how fast was he going? What was the rate? And then there's all sorts of variations. If you look in the Common Core standards, grades 6 and 7, it's quite explicit. In the way a lot of times that we've taught, including the way a lot of books have it, these three kinds of questions, how far in a given time, how long to go a given distance, how fast is he going, are treated as three different kinds of problems, and each has its own method of solution. And they're often pages and pages apart. If you look in a Japanese book, these will be in the same part of the same page. Because these are three questions about a single relationship, which is a relationship between time and distance. And in the Common Core, it's clear that the subject that you're teaching is this relationship and all the questions that you can ask about that relationship and the role of a constant rate in governing that relationship and how you can represent it in a graph, as our Dodger fan says.
Could you extrapolate and say what is like if he changes his speed, like he gets tired? So what are some of the things that we'll have to later down the road?
Yes, that sort of thing is what modeling is about. And modeling is both a practice standard and it's explicit, particularly in high school, that kids be taught modeling. So that is not part of the proportional relationship curriculum, although it would be useful because kids need to learn by contrast. Not everything is proportional, and it will help them understand constant rate if they have examples where it's not constant. But modeling is directly about how you use mathematical representations to represent things like that, things that are messy like the world. So yes, that's in the standard. It might not be in this lesson. So this is another example of how coherence reduces the amount you have to learn, but you have to go a step deeper into the mathematics. This is a proportional relationship. You can make tables that show the paired values. Those paired values are related to the ordered pairs in the graph. What would be the axes of your graph? Where is the rate on the graph? It's very coherent, but we've broken it up and fragmented it. Okay, I'm going to skip some things, some other problems. Just quickly about focus. Let me see where we are. Okay. There's been a lot of pressure on teachers So I've told you the main way in which we make the curriculum mile wide, inch deep already. We do it by teaching answer getting instead of mathematics. The butterfly method, it makes the curriculum shallow and wide. Teaching 3 different methods for 3 different kinds of problems instead of one relationship makes it shallow and wide. But the districts and state make it shallow and wide by telling teachers to cover. Cover is a synonym for mile wide, inch deep. When I hear cover, I cringe, I wince. Focus is the word. In TIMSS, the TIMSS test has more on it than any country teaches. So all kids, when they take the TIMSS test, see things they haven't been taught. And if you think about why they do that, to compare countries, you'd have to do that. But the hypothesis was put forward a while ago that maybe some countries are doing better because they match what's on TIMSS better. And so they did a study of that. And they found, that year they did the study 05, that must have been the 02 TIMSS, that the top-ranking country was Hong Kong. It omitted 48% of what was on the test. It means half the items on the test, those kids had never been taught. And that was not unusual. Most of the Asian countries are around 50%. The country which covered more than any other country, 83% of the test was covered by the U.S. We only left out 17. So our kids had been taught more of what was on the test, and they were a laggard. Covering does not translate into test performance. This is not the only study that shows learning translates into test performance. Learn some things well will give you a higher test score than covering everything. This is, again and again, I'm going to keep coming back to this theme, which is the same theme we heard in this morning's keynote, of the need to slow down. When we watched the lessons in Singapore, then we were talking afterward over a beer, one of the American teachers said, "How can they teach so slowly? Those lessons are so slow." They were slow, but every step was a real step. There was no wasted time. Japan, during lesson study, the Japanese guy who was running it turned to the Americans and said, "What did you see in our lesson?" And the teacher said, "All your teachers are so patient." And he goes like this: "We teach at the speed of learning. It does not require patience to teach at the speed of learning." And the thing that really came home to me is the speed of learning is much slower than we teach. If you look at the data, our mean score is lower, but even more dramatic is our dispersion is much greater than anywhere in the world. You're on a class trip, kids behind you are spread out too much. If you have common sense, you'll stop, you'll get them bunched up, and you'll go more slowly. Spread out too much is a symptom that you're going too fast. If you don't have common sense, instead you have political posture. If our mean score is too low, we'll speed up. And that's just what Americans have done. Our problem is we're going too fast and we're teaching too much. And our response has been, teach it at an earlier grade. Wrong move. There's very little mathematics that for most people is more important than the mathematics of middle school and Algebra 1. The more advanced mathematics that comes later is not as important. And yet what we've done is skip the more important math to get to the more advanced math. College faculty forever, as long as ACT has been doing this study, when they're asked what's the most important thing for incoming freshmen, have checked the topics that are in Algebra 1 in middle school, not the topics in pre-calculus. And high school teachers, since the beginning of this study, have always checked more advanced equals more important. if you're not a STEM major, the most important math you're ever going to use is in middle school. It's percents and rates and ratios and that stuff. And if you are a STEM major, more important that you have a deep understanding of algebra and basics of functions than that you rush ahead to advanced topics. Grain size is another. We tried, because the states urge us, to make all the standards the same grain size. And it was torturous. And we finally said, why is it so hard? And then we realized it's hard because it's wrong. The size of the standard should match the grain size of the math that it's about. And it made us very alert to what the grain size of mathematics is. And one of the things we discovered is it does not break down into lesson-sized pieces. That's too small. Fortunately, it does break down into chapter-sized pieces. You could teach a coherent body of mathematics in one chapter in 2, 3, 4, 5 weeks. That's a good amount of time to teach something in mathematics. If you're going to try to teach in one lesson, you have to make a lot of assumptions about what your students already know and what they're going to learn next week. Lessons are important, but if you're working collaboratively as teachers on mathematical content, which you should be doing, it's much more productive to work at the chapter level. So let's get together and talk about this upcoming chapter and what's the mathematics we want them to walk away from this chapter with. That's much more productive than having that conversation about the mathematics of any individual lesson. And in terms of having a sense of direction, a mathematical sense of direction while you're teaching the lesson, it's much more reliable for that sense of direction to come from the chapter than from the particular lesson. So that means putting the standard you're teaching today up on the board is nonsense. And I say that I spoke to all the principals in LA over the last few months, and I always say that. It does not get applause from them. If you want, what I tell them is if you want something up on the board, have them put a cluster of standards that the chapter is about up at the beginning of the chapter, talk about the chapter, and then leave it up there all chapter long. So I'm sorry, but you're going to have to write more stuff up there, but you only have to do it once a chapter. All right, so I want to... You all know about the practice standards. I'm just going to make a remark about them and then get to my punchlines, which you've already heard. These practices are standards. They're enumerated. They're supposed to be assessed. Park and Smarter Balance are doing backwards somersaults, trying to figure out how to assess these. When you look at what we did here was try to define mathematical expertise that crossed with all the content and the content standards. So this is global expertise that students develop over time. But when you look at them, make sense of complex problems and persevere in solving them. Well, it's obvious when you read this is on page 6, when you read the 2-paragraph description of what that means, it's not about solving rehearsed problems. It's not about what you do when you've been rehearsing a problem and now you have some more to solve. This is about what you do when you get a problem you don't know how to solve. What we've inadvertently been teaching in the American tradition is, if you don't remember how to solve it, quit. But inadvertently, that's it. Well, you know what? That's bad character. That's not the character that we want people to have. If it's a problem and you don't know how to solve it, you should persevere. And that's what this practice standard is saying. So these are not only about mathematical expertise, this describes the content of your mathematical character. And to teach character, you have to model it. All right, I need to skip stuff. The slides will be up on the Curtis Center website. There's lots of good things to talk about. But I want to just do one last point because it's we've talked a lot about this one. I want to just talk about this one. In an American classroom, teacher asks a question, and you get this, ooh, 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 from some of the kids. What is the ooh, ooh, ooh doing to the other kids? In Japan, when the kids are working on a problem, if they finished, it's considered rude to put your pen down. Out of the side of your partner's eye, they should not realize you're finished. The teacher cold calls in Japan, not every single time, but especially at the beginning. Okay, students, I'm asking the question. I want you all to prepare an answer. Make some notes in your journal as part of your preparation for the answer. If you want a diagram, put it in your journal, and we'll put it on the board. Now, prepare your answer. Now, in that setting, the teacher will decide who to call on. So everyone's getting ready to get called on. In the ooh classroom, some of the kids, many mathematicians have, in their autobiographical musings, will remark that I didn't realize I was good in math, or I thought I was bad in math because I was slow. That's what they're doing. They're thinking about lots of stuff about the problem. I didn't realize it until algebra or until geometry or until something difficult came up. So we're misleading good mathematical thinkers who are thinking thoroughly and slowly, and we're misleading fast answer getters. And we're misleading the kids who just need more time to think it through. We're making everybody think some kids are good at math and some kids aren't. I have a granddaughter who wants to be in the crowd, but she's not. So she does what many kids do. She just oohs anyway. And then when the teacher calls on her, she says, 6? And then she can see by the teacher's expression, 8? The ooh behavior, the ooh culture is teaching her she's not good at math. It's teaching her to give up on herself. It's teaching her to quit. I can't express how damaging the ooh culture is, and yet it's commonplace in this country. It's one of the easiest things to do for a group of teachers in a school. This is best done by a school full of teachers, not 100%, but most teachers. We're no longer going to be an ooh school. We're going to cold call to get discussions going. Once they get going, you can be more natural, but getting the cold call going. There's a second part to that, just as important, maybe more important. Japanese kid gets called on. He doesn't explain it to the teacher. He turns around and explains it to the class. Your response in Japan is an explanation, not an answer. And there's an explanation. The criterion for whether it's a good explanation is, do the other students understand it? An American kid is just answering the teacher as the audience. And so if they're not sure, they'll be vague. They've perfected it because they know teachers will see what they want to see. And the goal of the American student is have the teacher move on to another kid, or think I'm smart, or think I was paying attention when I wasn't. It's a shallow relationship. In Japan, when you're called on, you explain to the rest of the class. And then the teacher asks, how many understood? You see the hands go up or not. And so one of the lessons I saw, they call on 3 different ways of thinking, 3 or 4. And they start with the easiest to understand way of thinking, which is usually a below grade level, use of below grade level math to solve a grade level problem, using skip counting to solve a rate problem in 6th grade. Nothing wrong with it, but it's not 6th grade math. And then they finish, the last one is using the grade level math, using unit rate, for example, if that's what you're trying to teach. So Kimmy gets up. This was actually an inequality problem. And Kimmy explains using inequalities and equations. The other kids didn't do it with inequalities. They did it with just recursive methods. Ka-chunk, ka-chunk, this one, and then this one, and then this one, and then this one, until they got the answer. They set up an inequality. Kimmy set up an equality. She explained it real fast. And the teacher said, how many understood? Hardly any hands go up. And then the teacher turns to Kimmy and goes just like this. Kimmy, you're supposed to be working on making your explanations better. And he calls on two kids who didn't raise their hands and said, help Kimmy make a better explanation. And when you think Kimmy has a good explanation, tell me so we can see if it's good. And later, they said it's ready, and Kimmy had her second try, her revision of her explanation, and more kids understood it. So this accomplishes so many things. It's this thing I'm talking about. The shift from explaining it to the teacher to explaining it so the other kids can understand. And with that, my time is up, so I'm going to stop. Thank you very much.